Hello and welcome once again back to part 4 of Gardening in a Changing Climate. Again, my name is Steve Savage, your host and guide as we continue our journey through Earth's changing climates. As you'll remember in part 3, we saw the last two mass extinctions, the Triassic and the Cretaceous. We compared mass extinctions to what is happening today, and we looked at human influences. In part 4, we will examine the consequences of proceeding as usual. So climb aboard and as our journey continues. A couple of housekeeping things. This one will run about an hour and a half roughly. It's a little bit longer. And the other thing is that I'm going to give you a lot of numbers. I've already given you a lot of numbers. It isn't anything new, but there's going to be a lot of numbers on this. And you'll probably say, Steve, you expect me to remember all these numbers? And the answer is absolutely not. I don't remember a lot of the numbers. I read them to you. But the important numbers I remember, and you might want to tag them. But the rest of them, it's more important just to remember what the trend is, either whether it's up or down, good or bad. That's the main thing to remember, not the specific numbers per se. Okay, so with that then, again, let's try to jump aboard and get this thing underway. So wherever we live on Earth, as you are well aware, the climate change is affecting us. The climate has never changed so fast as it in all of human history, in fact, in all of probably Earth history, as it is today. And I want to give you a quote again. This is from a lady named Catherine Heo. And she's a doctor of atmospheric science, atmospheric physics, one or the other, and I believe she's at Texas Tech. And what she says is, those who doubt offer arguments such as, the climate always fluctuates, but it's so cold today. Those scientists are fudging the data. Never mind that according to orbital cycles that drive ice ages, we should be cooling, not warming. And remember, we talked about that. That individual cold days don't disprove decades of warming, or that scientists really and truly have no reason to lie. So she asks a question then, why is it so difficult to accept that our climate has been altered and we are responsible? And she answers her own question, because if we don't accept it, then we don't have to disrupt our way of life to address it. It's easier to say, the problem isn't real, than to admit the problem is real, but I don't want to sacrifice to fix it. And that's the end of that quote. Let me quote our good friend again, Peter Brennan. The problem we have created is that we are not just warming or polluting or acidifying or overexploiting. It is that we have created a perfect storm of all of this stuff and doing it all at once, just as hard and fast as we possibly can. We probably won't go extinct, at least not in the short run. We are pretty adaptable, but quality of life for most humans will go down the tubes. Looking back on human development, the last ice age ended about 12,000 years ago. Our civilization developed and continues to develop in an interglacial period, an uncommonly pleasant climate window that has existed for 10,000 years. During this time, all industry and agriculture developed. Indeed, within this brief window, all recorded history has occurred. End of quote. Can we count on that to continue? Given current trends, probably not. So what might the future hold if we continue as we are today? Well, again, let me quote Peter Brennan. To quote, today we are at 1.1 degrees Celsius, and that was in 2019, and it's true, I think, still right now in 2020, warmer than the pre-industrial global temperature. If we burn all remaining fossil fuel reserves, Earth will warm about 18 degrees Celsius. That is a temperature spike greater than occurred in the Permian extinction. Remember that one? Even an increase of 1/4 of that, 4.5 degrees Celsius, creates a world unseen by humans. And we're almost 1/4 of the way there. As we have seen, the last time Earth was 4 degrees Celsius warmer in the Eocene epoch 34 million years ago, there was no ice on Earth. Forests grew at the poles and sea level was 260 feet higher. It will take about a century of fossil fuel burning at our current rate to get somewhere near a 7 degree Celsius increase. That would be catastrophic. But here's the rub. Avoiding that kind of increase requires leaving 80% of current fossil fuel reserves in the ground. Are we prepared or willing or able to do that? End of quote. And new projections, and the new projections 2019, indicate we will have to reduce carbon dioxide emissions to near zero by mid-century and start to remove carbon dioxide post-2050 in order to avoid the worst consequences of higher atmospheric carbon dioxide. And a report just released on September 10th, this is September 11th, I'm recording this, 2020, says there is a 25% chance that average global temperatures will exceed a 1.5 degrees Celsius rise above the pre-industrial revolution temperature by 2025. Remember, we had a goal that we were trying to limit the increase to at or below 1.5 degrees Celsius. Previous reports said the rise would not occur until sometime between 2030 and 2052. Well, we are well ahead of that schedule. So let's look now at some of the consequences of our past fossil fuel burning and the resultant impacts on Earth. These are things that are either happening now or will happen in the future if we don't stop adding carbon dioxide to the atmosphere. So the first one then is increasing atmospheric carbon dioxide and warming. And here's come the numbers, folks. Atmospheric carbon dioxide levels have risen from pre-industrial levels of 270 to 280 parts per million to about 415 parts per million in 2019 and 417 parts per million by the middle of 2020. And those numbers you might want to remember. These are levels, again, not seen since the Pliocene 3 million years ago, at a time when the Antarctic ice sheet was much smaller than it is today. Carbon dioxide levels are rising at a rate of about 2.5 parts per million per year. And remember, in 2018 to 2019, it actually was 3.75 parts per million. It would be much worse without the oceans, which absorb 40% of atmospheric carbon dioxide, or about 90% of the heat generated by that carbon dioxide. Without ocean absorption, atmospheric temperatures would be already be much worse than they are today. There are signs, as we've discussed, that the ocean may be nearing the limit of its ability to absorb carbon dioxide. That is, it would still absorb the carbon dioxide quantities that it is today, but because we keep putting more and more in, it can't keep absorbing all that excess that we keep adding. Okay, and so what that means then, with decreased absorption, atmospheric temperatures will increase more rapidly. And as we've seen, ocean carbon dioxide absorption comes at a cost, and we'll talk about that a little bit more shortly. If carbon dioxide emissions continue to increase, the Antarctic will go further back in time, perhaps to the Cretaceous period, 66 to 145 million years ago, or the Paleocene-Eocene epochs, 34 to 66 million years ago, when Antarctica was ice-free. Forests covered most of the continent, and sea levels were their highest in history, as much as 600 to 800 feet higher than they are today. 2017 was the warmest year ever recorded since record keeping began, about 200 years ago. It beat records set in 2015. In fact, as we noted, 18 of the last 19 warmest years on record have occurred since 2001. And I wouldn't be surprised to see 2020 set yet another record. Both poles have experienced the most rapid warming, and that's pretty important, as we'll again see just a little bit down the road here. So what about ocean warming? And pardon me for sniffling a lot, the smoke is really irritating me a whole bunch. Sea surface temperatures are at record highs. An interesting side note is that the Gulf of Maine is warming faster than almost any other ocean region, which is playing havoc with the lobster industry out there, because remember, lobster like cold water, and it's warming. Warming water expands, contributing to rising sea levels, which will increase coastal flooding. In fact, it already has. About 170 U.S. coastal communities will experience chronic flooding within the next 20 years. And again, many of those are already experiencing chronic flooding when they get a high tide coming in, or the higher tides. Even the U.S. Navy base at Norfolk, Virginia, which is one of the largest Navy bases in the world, is in danger of being flooded out. They may have their ships sailing down the streets of Norfolk if they're not careful. So warming ocean water is coupled with an influx of agricultural fertilizer is causing massive algae blooms. Again, we've discussed this. You probably read it in the paper occasionally. And those blooms, again, we've discussed, can lead to anoxic conditions and dead zones in the ocean, which they already are. And finally, ocean warming leads to reef die-off through a process called bleaching. Bleaching occurs because coral lives in a symbiotic relationship with bacteria. The bacteria living in the coral produce food for the coral. In turn, the coral provides habitat and protection for the bacteria. As the ocean water warms, the bacteria secrete a substance, and now I don't know what it is, that causes the coral to expel the bacteria. No bacteria equals no food. No food, the coral dies. Bleaching, it's called coral bleaching. And bleaching events have occurred in 1998, and they occurred again in 2010, but the worst was in 2014. This event lasted for 3 years, from 2014 into 2017, and harmed more than 70% of the world's coral reefs. 2/3 of the Great Barrier Reef was reported as dead or severely bleached. And I'll tell you of my account with that. Again, my wife and I were touring New Zealand and Australia in the summer of 2014. We really picked a bad year. In New Zealand, the summer was colder than normal. We were freezing to death because we were dressed for summer. We crossed over to Melbourne, and we got there, and we were there several days. And the day before we left was the Australian Open, and they were forecasting temperatures of 110 degrees. So we flew up to Cairns, which was where the jump-off point for the Great Barrier Reef, because I wanted to do some diving there. My wife doesn't do that; she shops, so she shopped. So I caught the hydrofoil out to the diving platform. Get out there. They serve a nice lunch, by the way. They have a little room that drops down below the platform where they have windows in it, and you can kind of look out and see the coral. And what I saw was pretty disturbing at that point, because it was all, what I could see was all white coral. And I couldn't see any fish, except I saw hundreds of jellyfish. So I went back up and got ready to go in, and they had wetsuits. And I said, hey, you think I ought to wear a wetsuit? And they said, oh, probably not. I said, what about all those jellyfish stinging? He said, oh, they hardly ever sting you. And I said, well, thanks very much, but I think I'll put the wetsuit on. So then I on into the water, and I get down there. And for as far as I can go, the coral is white, which means it's bleached. No fish, except for lots of jellyfish and 2 sea bass that were kind of cruising around the area. That was it. So that was my experience then with coral bleaching in 2014. There are estimates that only 10% of reefs will survive past 2050. An interesting new finding is that over the next few decades, the warming and acidifying ocean will turn bluer. Yay, right? The water color itself won't change, but rather the population of phytoplankton will decrease. And remember, phytoplankton contain chlorophyll, which adds green to the ocean, changing its color. Fewer phytoplankton equals less green, equals bluer water. So the bad news about that, and the nice news, I guess, is the water's going to be a little bit bluer. The bad news is the bluing indicates a collapse of the food chain, and we know where that leads. Let's look at ocean acidification. Again, the oceans absorb the carbon dioxide from the atmosphere, delaying atmospheric warming, but coming at a price. And the price is ocean acidification. Adding carbon dioxide to the ocean increases its acidity. Acid water dissolves calcium carbonate. Remember, we talked about calcium carbonate, removes it from the water and locks it up as something called a bicarbonate, which is totally useless to shellfish, to coral, and to like krill, anything with an exoskeleton for building those skeletons, shells, and restructures. Destruction of the reef ecosystem then, which follows therefrom, the combination of ocean warming and acidification will be devastating to the reefs and other shell-forming creatures, as we've already seen. With increasing acid water and bleaching, the reef system will eventually collapse, as does much of the plankton and the krill and that sort of thing that form the base of the food chain. Loss of reefs could lead to loss of 30% of marine species. The structure of the food chain will result in the loss of most of the rest. Let's talk a little bit about deglaciation. So atmospheric warming is causing rapid ice melt. Almost all glaciers worldwide are in retreat. 1/4 of the Himalayan glacial ice has been lost over the past 40 years. The melt rate for the period 2000 to 2016 was double the rate from 1975 to 2000, and that loss is accelerating. Temperatures today for the region are 1 degree Celsius higher than for the 1975 to 2000 period. More than half of the Himalayas glacial ice, remaining ice, will be lost by 2100 if we reduce carbon dioxide emissions. If we don't, that loss will be around 2/3. The melting of Arctic ice is occurring 60 years sooner than the models predicted. You know, and everybody back in the day, earlier days when the models were predicting this, and then, oh, it's not going to happen. It's not going to be that fast. Well, it's going to be that fast. In fact, it's faster, 60 years faster than predicted. Between 1962 and 2006, glaciers melting in Alaska now alone, lost more than 440 cubic miles of water. That's nearly 4 times the volume of Lake Erie. Greenland's ice sheet is at its smallest volume since the 1950s when measurements began. Its melt rate is increasing. In fact, it's melting 4 times faster now than in 2003 and 6 times faster than it was in the 1980s. That ice sheet has existed for 2.4 million years. It was actually growing in the 1970s. Mass loss began in the 1980s. If it all melts, it would raise sea level by a little bit better than 24 feet. From 2000 to 2010, just some gee whiz numbers here for you, Greenland's total ice loss was 412 trillion, that's with a T, pounds. From 2010 to 2018, the loss rate accelerated to 631 trillion pounds. In Antarctica, several ice sheets are in danger of collapsing, and such a breakup would allow continental glaciers to slide into the ocean. The West Antarctic ice sheet is the most troubled. And when we're talking about this, we're talking about ice sheets. Those are on land and they aren't moving, which we don't want them to move. They can be up to 2 miles thick or more. Glaciers are, again, ice sheets or towering things that actually move. And we talked about a glacier. Glacier is just an ice sheet that is moving. And then we also talk about an ice shelf or the sea ice, which is ice that's sitting on the water itself along the coast, and sometimes for quite a distance off the coast. So we're talking about 3 different things here. Keep that straight if you can. So the West Antarctic area appears to be especially sensitive to climate change. In fact, it is one of the most rapidly changing areas on the planet. Once thought to be secure for the next 1 to 2 centuries, the ice sheet is now showing signs of an early breakup. And much of that depends on the unstable Thwaites Glacier. Now, the Thwaites is a tidal glacier, which means it comes right down to the coast. And we're going to talk about tidal glaciers a little bit later on today. So it's a tidal glacier sitting right on the coast. It acts as a stopper, holding much of the West Antarctic ice sheet in place. If Thwaites collapses, so does much of that ice sheet. And then it slides into the ocean where obviously it melts. And that would add as much as 11 feet to sea level rise. There are troubling signs for Thwaites. It's held in place by two things. First of all, a ridge on the seafloor under the ice, which grounds the glacier. In other words, the bottom of the glacier is hung up on that ridge line. And it was thought that would keep the glacier in check. But recent, I'm talking 2018, findings show a huge cavity has opened under the glacier. It probably indicates that the glacier is melting from the bottom even faster than predicted, and it's due to the warming seawater, which is coming up under there and eating it away. In fact, just yesterday, September 10th, 2020, I read that now there's even more concern about Thwaites because the sea level, the ocean depth there is deeper than they thought. So if that it indicates so it allows more water to get under the glacier to melt it, and so the melting there could be even quicker, which would result in even an earlier degrounding than what they were thinking just recently. So not good news. The ice shelf itself is holding the glacier back. Remember the ice floating on the sea? But that is retreating at a rate in excess of 650 feet per year. If the cavity and retreat of the ice shelf results in degrounding, the entire Thwaites could collapse in as little as 50 years. And that then would allow all that West Antarctic ice sheet to slide off Antarctica into the ocean and melt. Between 1992, some gee whiz numbers again, and 2011, the Antarctic melt rate was 84 billion tons per year. By 2012 to 2017, the rate increased to 241 billion tons per year. Over 3 trillion, with a T, tons of ice has disappeared between 1992 and 2017. So let's take a look then at melting permafrost. Again, the poles are warming more quickly than the rest of the Earth, and more quickly than models have projected once again. In the Arctic, summer ice is disappearing and winter ice has decreased. And this is just from this summer of 2020. In the Canadian Arctic, temperatures in 2020 were 9 degrees Fahrenheit, that's 5 degrees Celsius, above the 30-year average. The Canadian Arctic's last intact ice sheet collapsed this summer, the summer of 2020. The decrease in sea ice allows the darker sea surface to absorb more solar energy, warming the water. Remember, the ice is nice and white. It reflects the sunlight and the sun's energy away, so the temperatures don't get so warm. But that water up there is more of a gray color, so it absorbs much more of the solar radiation on it, and it warms the seawater. So less ice reduces the amount of solar radiation reflected back into space, causing additional warming. Additional warming of the water causes more sea ice to melt. So less solar energy is reflected back into space, more is absorbed by the water, it gets warmer, more sea ice melts. It's a feedback loop, and it just keeps feeding on itself and feeding on itself. That's why you're seeing the sea ice, particularly in the summer, melting more and more and more each year. So the net effect then is increasing overall warming of both the air in the Arctic and the ocean. While the Earth again has warmed by 1.1 degrees Celsius since the beginning of the 20th century, the Arctic has warmed by 1.6 degrees Celsius over just the last 50 years, and that was 2012 data there for that 1.6. So it's been 8 years. I'm sure it's even warmer than that now. Warming air is also melting the permafrost. Now, I don't know, I assume most of you know what permafrost is. Some people think it's just frozen dirt. Well, yeah, it is frozen dirt, but there's also a lot of dead plant life and animal life in there too. It's all frozen. It can't decompose because it's frozen, just like throwing it in your freezer, okay? But what's happening is that warming air is melting the permafrost, which allows the bacteria then to begin breaking down all that organic matter that was previously frozen. And that then releases, remember we talked about this, decaying plants release carbon dioxide back into the atmosphere. And worse yet, methane. Methane, remember again, is a greenhouse gas, and depending on whose source you read, it's anywhere from about 25 to 80 times more potent than carbon dioxide. Although it constitutes only 1,800 thousandths of the atmosphere, it accounts for 20% of the atmosphere's overall warming potential. The Arctic permafrost contains much more carbon than once thought, about as much carbon as the atmosphere contains today. A widespread thaw then would accelerate global warming, and thawing is occurring at a faster pace than predicted. It's been shown now that for every 1 degree Celsius rise in Earth's average temperature, permafrost may release the equivalent of 4 to 6 years worth of coal, oil, and natural gas emissions. And that's double to triple what was thought only a few years ago. Within a few decades then, permafrost could be as large a source of greenhouse gases as China is today. And China is the world's largest emitter of greenhouse gases today. These changes in the Arctic will influence global circulation patterns in both the atmosphere and the oceans, and we're going to talk about them, as you can see on this slide, a little bit later on. What about rivers running dry due to loss of glaciers? The loss of glacial ice in the mountains could have catastrophic effects on the availability of fresh water for drinking and agriculture worldwide, as well as transportation of goods. Because remember, many of these major rivers, the Yangtze, the Yellow, the Mississippi, the Irrawaddy, all these are large rivers which are fed by glacial melt. And they're big, ocean-going ships can actually get up into them for quite some distance, carrying goods either up the river or back down the river. So many major rivers then are fed by glacial melt and kept flowing year-round by these melt waters. Lose the glaciers and flow will drastically decrease during the summer months when water is needed the most. Think of, if you want to get a little tiny picture of what that might look like, let's look at the waterfalls in Yosemite. You go there in the spring, the snow is melting, and they're tremendous, lots of water coming over, they look fantastic. Go there in the late summer after all that snow is melted, and there are more or less trickles coming over there. That's the same kind of impact then that we'll see if these glaciers melt and we no longer have those meltwater to keep the rivers flowing at a good rate during the summer months. Obviously, in commerce along these rivers will be negatively impacted as well. What about glaciers locally then? Well, in the not too distant past, there were actually 7 active glaciers in the Sierra Nevada. And again, remember, an active glacier is defined as an ice field that is moving. Within the past few years, the active glacier count in the Sierra decreased to 2, the Lyell and the McClure. The Lyell over the past 130 years, from 1883 to 2015, shrank from an area of about 1/2 square mile to 66 acres, which is a loss of about 78% of its surface area. The McClure shrank from 99 to 33 acres over that same period, which is a reduction of about 2/3. Recent measurements, and these are 2017 measurements now, indicate that the Lyell is no longer moving, while McClure continues to move at about the same rate as measured by John Muir 150 years ago. And when he measured it, it wasn't moving very fast, but it was moving. So technically, it's still a glacier. So we're down now to 1 glacier in the Sierra, and that won't be a glacier much longer. At the current melt rate, both Lyell and McClure will be gone sometime between 2030 and 2040. That's the projection right now. These two glaciers, or now one glacier and an ice field, form the headwaters of the Tuolumne River. So their loss affects the river and its ecosystems that depend on them. As they melt, the resulting meltwater sustains the base flow of the river in late summer and fall. During the drought years from 2012 to 2015, glacial meltwater may have contributed up to 90% of the flow in the Tuolumne. What will the base flow be when they are gone? And what will that mean for the Hetch Hetchy Reservoir and for San Francisco that gets its drinking water from it? Temperatures across the Sierra are warming. The snowpack is shrinking and melting earlier, and increasingly winter precipitation arrives as rain, not snow, particularly in the lower elevations. 15 to 25% of the spring snowpack is already missing in most years. At our continued rate of carbon dioxide emissions, the Sierra snowpack will decrease by 48%. That's a projection by 2100. But during drought years, it could decrease by as much as 83%. There will also be wild swings between drought years and wet ones. And we've seen that. It's already been happening. Wet years could see more rain than snow, or worse, rain on snow events. And that is a real problem then for reservoir management. Remember, the reservoirs exist to catch, for flood control, to catch that water coming down, but also then to store that water so we can have it for use in the summertime. When you get a lot of rain coming down, they have to release water out of those reservoirs or keep them low to absorb that rainwater so it isn't coming down and flooding us, all right? With more of the precipitation falling as rain, you're going to have more flow coming down, which means you're going to have to maintain those reservoirs at a lower level. If you get rain on snow events where you have a snowpack that's already there, then it rains, you not only get the rain, but the melted snow coming down, which is even worse. So they're going to have to try to keep that reservoir low, letting out most of the water to catch the water that's coming down, and then letting that out to catch the next one. The problem is if they let that water down to catch the next one, and the next one doesn't come, the rest of the winter remains dry. Now they've let almost all their water out. So now we don't have as much water for the summer. It's a real management problem. On the other hand, if they don't let out enough and then the reservoir fills and it overtops the dam, that can lead to dam failure. And then like Sacramento washes out into the bay. It's a real problem. And I hate to be the people trying to manage that problem. So Sierra temperatures then are projected to increase from 7 to 10 degrees Fahrenheit, and snow will likely cease to accumulate at elevations below 8,000 feet. So again, the reservoir management problems, and that then it can lead to increased groundwater pumping in drought years. Increased pumping could in turn lead to deeper wells, which require more electricity to pump, which again maybe involve burning more fossil fuels to generate that electricity, which more carbon dioxide. And then many of the well pumps are actually diesel generators or diesel pumps. So you're burning diesel fuel at a higher rate, again, putting more carbon dioxide into the atmosphere. Rivers and creeks, it may also lead to rivers and creeks that no longer flow year-round, subsidence or subsidence, and potentially aquifer collapse. And let's talk about that just a little bit. So what is an aquifer? It's underground water, obviously it's groundwater. A lot of people think that an aquifer is kind of like an underground lake. You know, you dip your straw into it and you suck out some water. That really isn't true. What it is, it's loose, rocky kinds of things such as gravel, sand to some degree, shale. All these things have large spaces in between the rock and cracks, and the water accumulates in those. It's the same as with oil. It does the same thing. Shale oil, it's the same idea. So when you drill down into that aquifer then, the hole you put in the ground has less pressure in it, and the water, then the hydrostatic pressure of the water pushes that water into the well bore, and then you pump the water out. And you can do that, and the aquifer will drop, but as long as you're getting enough rain or snow melt or whatever to recharge the aquifer, everything is great. You can pump water forever. The problem comes is when you start drawing more water out than is being put back in, and that means the aquifer level, the groundwater level begins to fall, which is what is happening throughout California today and a lot of other places, in not only the US, but in the world. So as that aquifer falls, then remember all that sand and gravel and shale is being held, the space is being held open by the hydrostatic pressure of the water. So as the water level falls, that begins to compress, subsidence. You're seeing that in the San Joaquin Valley, particularly right now. You keep reading these accounts where the roads are falling up. So one part of the piece of the road drops down 3 or 4 inches or a foot or whatever it is, and the other one stays up. And also the aqueducts, both the federal and the state aqueducts that take water down to LA. Those two are getting out. They run, at least as far down as the Tehachapis, they run by gravitational flow. When the aquifers get out of alignment, the flow doesn't work anymore. A real problem, subsidence. So we're also seeing, if you continue to pump that thing down and you don't recharge it, and it gets lower and lower, at some point you can deplete the aquifer, but you don't even have to get it totally empty. If you just get it far enough down, what happens is the aquifer collapses. So all those spaces, then it's all crushed together. You can recharge an aquifer as long as there's enough pressure in there to hold those spaces open. But once the aquifer collapses, you can no longer recharge it. It is gone forever. All right, and that is what's happening or projected to happen up in the upper Midwest in the Ogallala aquifer, which is being pumped, has been pumped for years and years for agricultural purposes there. In fact, if you fly over western Wyoming and eastern Nebraska, you see those crop circles out there where they've got a big irrigation arm and it swings around and around and waters. That's drawing water out of that aquifer, and it has been for years. And those aquifers are getting very low. They're doing it to grow corn, which is don't even get me started on that. It's really, corn is not a very effective product to be spending precious water on, trust me. So there's a real risk that aquifer is going to collapse. Okay, the other thing that you see down in the southern San Joaquin Valley is that they fertilize down there a lot for gardening or for crops, and when they take that water and put it on there, and they put nitrogen fertilizer on there, and they get too much. Remember, we talked about that, and I think we will again. That water seeps the nitrogen fertilizer down into the aquifer and pollutes it with nitrogen compounds. Another thing is down there, the soil has a lot of arsenic in it, and the irrigation water then dissolves that arsenic and puts it down into the aquifer too, which poisons the aquifer. And you probably read about towns down there, they can no longer use their wells. Instead, they have to import water in tank trucks or go out and buy bottled water. That's the problem there. Still, another thing that you can look at is the Cosumnes River up here, right in our own backyard. It's the only river that flows down off the Sierras on the western side of the Sierras that doesn't have a dam on it, so it's a free-flowing river. In years past, it used to flow year-round, pretty much. Now, in the summertime, it obviously was not a raging river. It was more like a big stream, but it still flowed. And the reason it flowed is the water table was high enough that water could percolate out through seeps into little creeks, into bigger creeks, into streams, and flow into the river. And that kept that river flowing throughout the summer. Most summers now, the Cosumnes no longer flows year-round. And the reason for that is, again, pumping. It's lowered the water table, the aquifer, down to where it's below those seeps, so they can no longer provide those little creeks and little streams which keep the river flowing year-round. So with that then, how about increased desertification? So the loss of river flows due to glacial loss will result in areas that were once verdant, either naturally or through irrigation, becoming increasingly dry. Water diversion to supply agriculture and human needs will increase even as flows decrease. And this will lead to increased groundwater pumping as the surface water dries up. And we've already talked about where that leads. Okay. So the natural conclusion to all this can be seen in a number of areas. One of these is the virtual drying up of the RLC. Now, most of you have never heard of the RLC, but it was a large inland sea in Central Asia. It was a sea. There were coastal towns on it. They sent fishing boats out to fish. It was an inland sea. It was fed. It's an interior drainage, so the rivers were flowing not out to the oceans, but into this RLC, which kept the water level up. Well, back in the days of the Soviet Union, the Soviets decided in their infinite wisdom that they were going to divert these rivers for agricultural purposes. What that did was it either decreased or totally eliminated the inflow of water that was keeping the RLC up. The result, the RLC began to evaporate. Today, if you happen to look at the RLC from a satellite picture, you would more or less call it the RL puddle. It's virtually dried up. There are no more boats going out to fish on the RLC anymore. They wouldn't even float. Okay. So that's one example. Another one is the Jordan River and the Dead Sea and the Sea of Galilee. Okay, the Jordan River feeds the Dead Sea and then on down into the Sea of Galilee. And it is increasingly being dammed and diverted for agricultural purposes and for drinking water and so on and so forth. The result is the RLC is dropping rapidly its level. In fact, there used to be coastal towns along the RLC, which were resorts. You know, people would go there because, you know, it's really salty and you could float and you couldn't sink and that sort of thing. All those coastal towns now and resorts are a mile or more away from the coast of the Dead Sea now. And it's very dangerous to go down there because it's an area where with the water out, you have lots of sinkholes develop. So driving a car on a road, sinkhole can open up underneath you, even walking. So it's really, really dangerous. And that shows you how much the RLC has sunk. And it will continue to go down, the level will go down, and maybe we will eventually no longer have, did I say RL, I meant Dead Sea. We'll no longer have a Dead Sea. The same fate is awaiting the Sea of Galilee, by the way. So let's look at something in our own backyard. All right. So back in the early 1900s, a guy in LA was looking for more water. What's new about that? They're always looking for more water. And a guy named Mulholland, have you ever driven down Mulholland Drive? Same guy. He looks around and he sees the Eastern Sierra with all these streams flowing down. And they're feeding into the Owens Valley and they're feeding into Mono Lake. And they're keeping Owens Lake kind of water filled and irrigating and repairing habitat along the streams is all nice. And it's keeping the water level in Mono Lake up also. So he says, that water's just going to waste. Let's dam those things up, make lakes, and we'll put a pipe there and we'll run that water right down to LA and we can have nice lawns. Yeah. So that's what they did. Well, Owens Dry Lake is Owens Dry Lake now. Lots of problems there with salt. When the wind blows, the salty soil blows all around. It's more desertized or desertified or whatever now than it was. And the Mono Lake began to drop, just like the Dead Sea is now. Dropping the level because the water flow into them was keeping the level up, has now been diverted. Well, some people got together who lived in the area of Mono Lake, around Lee Vining and so on. They got together and they decided we need to do something about that or we're going to lose Mono Lake. And so they formed something called the Mono Lake Committee. And I'm telling you this now because later on in part 5, we're going to talk about what you can do. This is what a group, initially a fairly small group of people did. They took the water district in LA to court to stop them from destroying Mono Lake. So at least leave some of that flow coming down to keep the lake up. And they won. And so now they decided the lake level could no longer, they weren't trying to get it back up to the level it originally was, but they're trying to get it up from where it was at the time. So maybe halfway up. And they got an agreement that says that you have to let more water flow in there to maintain that level. Now, in a really wet year, they get more water and it comes up above that level. A really dry year, it may drop a little below, but they're trying to maintain this level. And it's a continuing fight because the water district in LA is still stalling and everything else. And so it's a continuing legal fight and probably will be forever to keep Mono Lake in existence. But that's what a group of people can do. Now, in the interest of full disclosure, I am a Mono Lake Committee member. That does not mean that I do anything, because I don't, other than I send them money. And if you contribute to the preservation of Mono Lake, you're considered a Mono Lake Committee member. That's my connection. But I do have an interest in Mono Lake and preserving it, so I'm not entirely a disinterested person when I tell you this, all right? So anyway, all of this then is the result then of increasing water diversion and pumping, and it's only going to get worse. Changes in global circulation, again, we'll look at those shortly, will also result in the spread of deserts and the creation of new ones. The Sahara is expanding now to the south, resulting in the loss of croplands, increased demand for water, famine, and mass migration. A lot of those people that are going up to the North African coast of the Mediterranean, then getting on those rickety boats to try to get over to the European coast of the Mediterranean, they're fleeing because of this loss of croplands and famine. That's what's going on for a good many of those people. What about the rise of sea level? Well, we've already discussed this pretty thoroughly. Suffice it to say that the continued glacial melting of the Greenland and Antarctic ice caps, and ocean warming will continue to cause sea level rises. Coastal flooding could cause massive population disturbances. As well, over half the population lives in coastal areas that either are or will be subject to flooding. So we will see a replay of the migration from the southern Sahara along most of the coastlines of the world eventually. So you're going to have a terrible mass migration and movement of people. And I don't know how you handle that. That's something we're going to have to figure out. Okay, so now we've gotten to changes in the global atmospheric circulation. So the difference in air and water temperature between the poles and the tropics, or the equator, equatorial regions, drives the global circulation of both the atmosphere and the ocean in ocean currents. Carbon dioxide increases in the atmosphere are warming both the air and the ocean. And the greatest warming, as we have seen, is occurring at the poles, which is decreasing the temperature difference between the poles and the tropics, both in the atmosphere and in the ocean. And this in turn is weakening these circulation systems, which are very important. So we're going to look at the atmospheric circulation first, then we'll look at the ocean, and we're going to talk about the northern hemisphere. Again, that is where we live, and the southern hemisphere is pretty much a mirror image on these circulation patterns. So, we'll talk northern hemisphere. So the warming Arctic then decreases the temperature difference between the poles and the tropics, which weakens both something called the polar jet stream and polar vortex. We'll talk about the polar jet stream first. And it's a fast-moving band of air, right about at 45 degrees north, roughly. It meanders, obviously, but right about there. And its elevation is somewhere between 25,000 to 35,000 feet, but the average is around 28 to 33,000 feet. So that is the polar jet stream. It flows from west to east all the way around the globe, okay? That polar jet stream acts as a steering mechanism for storm systems, determining not only where they go, but how fast they move. And what it has, again, remember that sinusoidal pattern we talked about back when? Well, for the carbon dioxide, well, it has these same waves in it. And where it waves up to the north in the northern hemisphere, we call that a ridge. Okay, if you're a meteorologist, you hear them talking about all the weather all the time. It's a ridge. Where it bends down, that's called trough. Where the ridges occur, it's generally fair weather, warmer weather, fairer weather. Where troughs occur, that's generally colder weather and stormy weather. That's where the storms are, okay? A weaker jet stream, which will happen because we have less of a temperature difference, which is what the driving mechanism is, increases the sharpness of the peaks, the ridges that is, and the valleys or the troughs that form the waves in the jet stream flow and which produce our weather. A slower jet stream produces, again, waves that are sharper. The ridges become higher, the troughs deeper, producing stronger high and low pressure systems. And sharper waves move more slowly past us. Sometimes they even stall in place. Truly extreme weather then tends to occur with stalled waves, as they can lock a region into either cold or warm air, prolonging cold or warm weather outbreaks, heavy snow or rain, prolonged dry periods, stalled hurricanes, and intense fire seasons. All right? Stalled cold air can make an area appear to defy the effects of an overall warming climate, and are often pointed out by global warming deniers as proof that global warming is a hoax. It isn't. The prolonged cold spells are a confirmation of global warming, not a refutation of it. Stalled waves have become common because of global warming. In fact, human-caused climate change has increased the likelihood of excessive weather events by roughly 50% over the past few years. We're seeing it outside today. The polar vortex, let's talk about that. This is another high-speed flow of air aloft that circles roughly, the poles roughly the Arctic Circle, okay, roughly there. What it does then is a strong polar vortex tends to constrain the cold Arctic air where it belongs, in the Arctic, right, north of the Arctic Circle. A weak vortex is less able to contain the cold air and keep it from plunging southward. Large waves on the jet stream can disrupt the polar vortex because by producing these, because they weaken it, and that allows the cold air outbreaks to come down, and that produces deep freezes and parades of snowstorms, much like what we saw, I think it was the winter of 2018, where the Midwest was locked in this cold weather, even the East Coast, and really frigid snowstorm after snowstorm was moving through. That, and you heard polar vortex every night on the news. That's what that was all about, folks. This whole weakening can also produce wild jet stream swings and that deliver heat waves to Alaska and the far north, and really cold to the far or to the south. And you see these anomalies where Anchorage and maybe even Fairbanks in the winter are warmer than Kentucky or Tennessee. It's weird. That's what happens. What about changing currents, ocean currents? So again, as with the atmospheric circulation, temperature differences between the poles and the equator drive the ocean currents. Salinity differences also have a very, very minor effect, although they affect sea life more than they do currents. The circulation carries warm water poleward from the tropics on the surface, and the circulation returns cold water equatorward from the pole via deep ocean currents. Evidence suggests that the Atlantic circulation is slowing down, and in fact has decreased by about 15% since the mid-20th century. It is believed the slowdown is caused again by climate change, causing Arctic seas to warm, reducing the temperature difference between the Arctic and the equator. Warming is also melting the Greenland ice sheet and mixing all that fresh water with the salty ocean water. That is altering the ocean chemistry by reducing salinity in the Greenland area, which somewhat weakens the driving mechanism. It's not producing the stratified oceans like we talked about earlier in part 1, I believe, or 2. It's not doing that yet, but it is affecting sea life there because a lot of the sea life lives in a balance with a certain level of salinity, and the level of salinity is falling because of this mixing in of fresh water. So what does that mean? Well, much of the Western and Northern Europe enjoy temperate weather due to the warm water brought northward by the Gulf Stream. The areas include Iceland, the British Isles, Ireland, Scandinavian countries, and Northern European countries as well. Reduction or cessation of that warm water flow could render many of these countries either uninhabitable or at least make life much more difficult. Changes in those ocean temperatures will also likely change precipitation patterns over much of Europe. Now, how much the changes are going to be and where they're going to occur exactly, no one knows yet. We have to wait a little longer for things to get a little bit more fouled up first. On the other hand, atmospheric warming may offset some of the warmth loss due to the slowing or loss of the warm ocean currents. So again, how's that going to play out? Don't know. The circulation is also crucial to fisheries off the U.S. Atlantic coast and other areas in the world too. Changes in water temperature and salinity could significantly alter them. Cod fisheries are already collapsing due to changes in water temperature and, of course, overfishing. Ocean currents worldwide will be similarly affected. What about something called changes in cloud distribution? Atmospheric warming affects different clouds in different ways. Some clouds enhance the greenhouse effect, tending to make us warmer, while others help to keep the planet cool. Cloud changes or really could changes in cloud distribution slow down or speed up global warming? That's a big question, a big issue. So the distribution of clouds and their altitude above Earth affects their cooling or warming effect. Low clouds generally produce cooling, while high clouds generally cause warming. With today's distribution of low and high clouds, the net effect is a slight edge towards cooling, so the cooling predominates. And that's helping, again, to keep the atmosphere a little less hot than it would have been, considering all the carbon dioxide that's in it. But changes in the atmospheric circulation caused by global warming is shifting cloud patterns toward the poles. As a result, the cooling power of low clouds is decreasing and, in fact, may begin to cause warming. Meanwhile, high clouds that produce warming are also moving poleward and increasing in altitude, and that process will accelerate their warming effect. Both those trends, then, if they continue, will accelerate planetary warming. What about wet bulb temperatures? The conundrum. Okay. So the first question you'll have is, what in the heck is a wet bulb temperature? All right. So a wet bulb temperature is if I take a thermometer and I put some wet cloth or gauze around the bulb, and then I put a string on it or something, and I whirl it around in the air, the lowest temperature that the thermometer will record due to evaporation from that gauze is called the wet bulb temperature. And there's actually an instrument that, I guess they would still use it, although now they usually use fans to do this, but it was called a sling psychrometer, which was basically what I just described. A thermometer, put wet gauze around it, and sling it in the air. And I've slung a bunch of sling psychrometers in my lifetime. So that was how they used to do it. Probably now they do it with fans and stuff. Maybe they still use those. So anyway, with that then, the wet bulb temperature is used to calculate the dew point, which is the temperature which, when reached, causes water vapor in the air to condense out, and the humidity, which is the percent of water vapor in the air versus the amount of water vapor that the air could hold, okay? So both those values dramatically affect how comfortable you feel for a given temperature. A high wet bulb, dew point, or humidity coupled with high temperature is at least very uncomfortable, especially any of you ever lived on the East Coast or the South in the summertime, and can be life-threatening as it reduces your body's ability to cool itself by sweating. Wet bulb temperatures above about 35 degrees Celsius, which is about 98 degrees Fahrenheit, are generally lethal to humans because it is not possible to dissipate heat, and therefore it is not possible to cool down. You sweat, but the sweat doesn't evaporate because the air is already saturated, okay? And so you can't, that's how you dissipate your excess heat, and you can't do that. So the heat just keeps building up, and you get heat stroke, and heat exhaustion, and then heat stroke. Modeling predicts just a 7 degrees Celsius increase in the average wet bulb temperature renders large parts of Earth lethal to mammals, including us. Rising temperatures coupled with rising wet bulb will likely render large parts of the Earth uninhabitable. In fact, the habitable zones may lie north of 45 degrees north. So you might want to start looking at Canadian citizenship in the next few years. So what about species extinction? We've talked about, speciation and lack of speciation. We've talked about that somewhat, especially the peril to the coral reef system posed by ocean warming and acidification. We've also talked about the effect of acidification on plankton and krill and the base of the food chain. And how about those lobsters up in Maine? There is also, we've seen the increase of algae blooms and subsequent anoxia and dead zones caused by overuse of fertilizers and deforestation that allow nutrients to be washed into the ocean. And we've talked about that quite a lot also. Overfishing is wiping out entire species as well. Look at the cod. Just cod though. On land, deforestation and habitat loss wipes out plant and animal species. Again, we've talked about that. Warming pushes many species to either move further north or to higher elevations to escape the heat. Those that cannot move quickly enough, or they run out of room to move up into the mountains because they've already reached the top, they die, they're lost. Plants bloom and fruit earlier in the spring or later in the fall as warming changes the growing season. And we'll talk about that more in part 5. We are creating monocultures over the entire globe. Hunting and poaching have and are continuing to destroy entire animal species. Dams and over-diversion of river flows destroy aquatic cycles and again, species. All of this leads then to species extinction on an ever-increasing scale. As an object lesson then, let's look at one species we are destroying by warming Earth. And it's important, not particularly for this species itself, but it's important because it shows the delicate balance that we all live in and need to survive. And the species I've chosen to talk about, because it's so clear-cut, is green sea turtles. And they don't develop into males or females due to sex hormones, as most animals, including us, do, and plants as well. Instead, it's the temperature outside the egg that determines the sex. 85 degrees Fahrenheit is the balanced temperature where there is a roughly even balance between the birth of males and females. A few degrees below 85 degrees Fahrenheit, all the turtles are born as males. A few degrees above 85 degrees Fahrenheit, and all the turtles are born as females. A warming world then is skewing sex at birth to almost all females. And if that, given a few more decades of warming, there won't be enough males to continue the species. Okay, and that's not only true for green, I think it's true for most of the sea turtle species. So what you say, who cares about green sea turtles? We can live without them. True. But loss of species due to climate change isn't confined to sea turtles. Survival of many species, including ones that are vital to us, is threatened by climate change. And as we have seen, lack of speciation often leads to mass extinction. What about the local consequences? Okay, and we're going to talk about atmospheric rivers, and you've probably heard of those before, referred to as, in California anyway, the Pineapple Express. So when you hear Pineapple Express, they're talking about atmospheric rivers. And we've discussed the effects of climate change on the Sierra snowpack, glaciers, and the consequences for runoff to fill our reservoirs and keep them filled. There is still this other phenomena that will be affected by climate change, and that is atmospheric rivers. Atmospheric rivers are high-level flows of moist air that moves from the tropics to the mid-latitudes. They are very common on the west coasts of continents such as the western US and specifically California. A typical atmospheric river can move as much water as 10 to 15 Mississippi rivers. And folks, that's a lot of water. California is very dependent on them as they produce anywhere from 30 to 50% of our winter rain and snow. Generally only a period of only 10 to 15 days each year, on 10 to 15 days per atmospheric river. So you get, and atmospheric rivers move around. They'll be here for in one place for 10 to 15 days, and may go away for a few weeks, and then maybe they'll hit someplace else for 10 to 15 days. That's what we're talking about. The largest of these storms occur about every 200 years. The latest studies suggest that they may become even larger and more frequent as the climate warms. Recently, a scale for categorizing the strength of each storm, similar to those used to classify hurricanes and tornadoes and earthquakes, has been developed. And that scale ranges from 1 to 5, with 5 being the strongest of it, and 1 obviously the weakest. And the scale bears a relationship then between the damage caused, with obviously more damage with a 5, less with a 1. With each increase in category, there is a 10-fold increase in damage. So it's not just as you go from one category to the next that the damage increases linearly, that is on a 1-for-1 basis, but instead it increases exponentially, just like the scale for earthquakes. Remember, we talked about that before. Since they're warm, tropical systems, much of the moisture falls as rain, with snow falling only at the higher elevations, typically above 8,000 feet. Future storms then will likely be more either all rain or perhaps rain on snow due to the atmospheric warming. Furthermore, a warming climate means the air can hold more moisture. Models predict the storms will deliver 10% more moisture than currently, and the number of storms will increase from an average of about 9 per year to perhaps 11 or more per year. The models also predict that occasional rivers will be bigger than the biggest historic storms. The most massive storm to hit California, at least since white people settled the Central Valley, occurred in the winter of 1861 to 62 and lasted for 43 days. It flooded most of the Central Valley, turning it into a vast inland sea. Sacramento was underwater for 6 months. It was the primary reason that the city was raised, part along the Sacramento River. You know, when you go to Old Town Sacramento now, the floor you see that is at street level now was actually originally the second floor of that building. The first floor is now below street level, and you can take tours to go down and visit that. It was also the impetus to start building levees to try to hold the river in place. The flow from the Sacramento and the San Joaquin rivers, the outflow was so great that it pushed the salt water out of San Francisco Bay, and for temporarily the bay was filled with fresh water. Applying today's classification, the storm would easily be a 5, if not even higher than that. Storms similar to the 1861-62 storms, but taking only 23 days versus 43 to deliver the same amount of water, are among the model predictions. This would produce sustained flooding covering most lowland areas in either northern or southern California, depending on where the storm struck. It could lead to the possible evacuation of 1.5 million people, probably kill thousands, think of mudslides alone, and result in $700 billion in losses. That's 3 times the estimated cost of a 7.8 magnitude quake in Southern California. So let's move on to something called, whoops, going too far there, something called the 2015 Paris Climate Accords. You've heard of those, right? You know, they're the ones the U.S. is pulling out of. The accord attempts to limit global temperatures increases to no more than 2 degrees Celsius by 2100, with 1.5 degrees Celsius the preferred goal. We've already increased by 1.1 degrees Celsius, and the rate of increase is accelerating. Little wonder, considering that we continue to dump carbon dioxide into the atmosphere at ever-increasing levels. This agreement is non-binding. It has no laws, no tests, no enforcement mechanisms. It is strictly voluntary. While the accords seek to reduce carbon dioxide emissions to limit atmospheric warming to less than 2 degrees Celsius, it now appears that cutting annual emissions worldwide to 0 by 2050 won't even be enough. We will now have to achieve net negative emissions, meaning removal of billions of tons of carbon dioxide from the atmosphere every year. We can no longer afford the luxury of dumping our garbage into the atmosphere, but instead we've got to start removing it. Warming, as noted, is currently about 1.1 degrees centigrade above the pre-industrial levels, increasing at about 0.2 degrees centigrade or Celsius per year. All that rate appears to be accelerating now to about 0.3 degrees Celsius per decade, not per year, per decade. At the higher rate, then, it's estimated we will have about 12 years, and that was from 2018, to act if we hope to avoid slipping past 1.5 degrees Celsius, the level regarded by most scientists as the furthest we can go if we hope to preserve life more or less as we know it. And remember, we just saw that now they're talking about going above 1.5 degrees by about 2025, as opposed to 2030 to 2040. Well, that from 2018, that was only about 7 years. And here they were talking 12 years. You see the acceleration that's occurring. With today's emissions of about 40 to 50 billion tons, 40 to 50 gigatons per year, there may be only about 5 years worth of carbon dioxide emissions left in that 1.5 degrees Celsius game plan. And in fact, that's exactly what's bearing out right now. Remember, 2025 from 2018? We are currently on track to reach 3.2 degrees Celsius of warming by the end of the century, with a range of uncertainty of somewhere from 2 to 4.9 degrees Celsius. And if you remember that graph we had back, I think it was part 2, where we had the carbon dioxide concentration on the vertical and the temperature, and we said for every doubling of carbon dioxide, we increased by 3 degrees Celsius on a global average. And it showed, again, that by about mid-century, or by the end of the century, we would be somewhere right around 4.5 degrees Celsius. Well, that increase, that tracks pretty darn close to what these studies have been showing as well. And in fact, at the current rate of emission and the current rate of temperature increase of 0.2 degrees Celsius per decade, we'll reach an increase of 2.9 degrees Celsius by 2100 if all pledged actions are implemented, and 3.2 degrees Celsius if we continue our current actions. Of course, that assumes that temperatures continue to increase at 0.2 degrees Celsius per decade. But in fact, as we know, that's increasing. In fact, it looks like it's gone up to 0.3 degrees Celsius per decade. So an increase of as much as 3 degrees Celsius by 2100 is certainly not out of the question. Warming greater than 3 degrees Celsius would be catastrophic, while greater than 5 degrees Celsius would pose an existential threat to much of the human population. Even if every country meets its most optimistic pledge, the planet will easily surpass 2 degrees Celsius increase. And remember, one of the biggest carbon dioxide polluters on Earth, the United States, number 2 after China, has pulled out of the accord, wants to increase coal mining and burning, repealed laws limiting wellhead methane emissions, wants to repeal other laws regulating coal-fired electric plant emissions, is trying to reduce automotive miles per gallon regulations, and wants to expand oil drilling in Alaska, the Midwest, and off virtually the entire US coast. And that doesn't even begin to account for the destruction of the rainforest and the burning of them, and also the wildfires in Australia that seem to be occurring with ever-increasing frequency. It also doesn't include a new EPA rule of repeal of clean water regulations that places limits on polluting chemicals that could be used near bodies of water. Remember the Clean Water Act back in, what was that, the 70s? Before that, you could throw a match in some of the rivers and it'd catch on fire. Most of the rivers were polluted. That Clean Water Act cleaned up those rivers so that now you can't burn them, at least, and most of them you can fish in them, and you can even maybe swim in them if you chose to do that. One immediate effect of the change would be that industries now can discharge potentially harmful substances into waterways. In other words, getting rid of much of the Clean Water Act and allowing industries to go back to doing what they were doing. So we risk our rivers turning back into the cesspools they once were. The question then is, can we muster the political will to pursue negative emissions while drastically cutting our current carbon dioxide input? It doesn't seem likely. Remember all those coal mines and coal-fired plants, power plants the Chinese and Indians and others are building or plan to build? To even reach a 2 degrees Celsius limit, we would have to reduce, I'm quoting now, let me go back. I'm quoting now, this is from Peter Brennan again. So to even reach a 2 degrees Celsius limit, we would have to reduce fossil fuel use to near zero by mid-century, begin to remove carbon dioxide from the atmosphere, and find 30 terawatts of carbon-free energy. That's more than double what we currently produce using mostly fossil fuels. All while the human population continues to add billions and developing countries become more middle class, increasing the demand for cars, energy, etc., etc. End of quote. Compare that to what is actually happening in 2017. India increased carbon dioxide emissions by 6.3%, China by 4.7%, the good old USA by 2.5%. Only the European Union held emissions steady. If we do somehow, limit the increase to 2 degrees Celsius by 2100, very major changes are already baked into the equation and will occur anyway. So even under the rosiest scenario, we will likely wipe out most coral reefs, destroy most parts of the world's rainforest, thereby decreasing the ability to remove carbon dioxide from the atmosphere, bring on massive extinctions, drown most coastal cities around the world, and that's to name just a few things. And much of that is already baked into the cake, folks. It's already there. Earth's climate, once again, is changing faster than at any point in the history of civilization and probably in the history of the world. Without a significant reduction in carbon dioxide emissions, average global temperature is going to exceed 2 degrees Celsius by 2100. And as we've seen, that is just catastrophic. And now I'm going to quote to you again from Peter Brennan. Quote, and it doesn't stop at 2100. There will be continued warming and sea level rises for hundreds, if not thousands of years until the carbon dioxide balance is restored, or at the very least, stopped increasing. We risk a return to the early Eocene epoch 55 million years ago, to a period called the Paleocene-Eocene thermal maximum, when the Earth experienced its hottest temperatures ever known, at least 25 to 26 degrees Celsius globally, probably higher than that, versus 14.9 degrees Celsius today. If we do mess it up and cause mass extinctions, it could take 100,000 years to get carbon out of the atmosphere and oceans, and 1 to 10 million years to rebuild the ecosystem. An ecosystem that might not include us. End of quote. And I'd like to quote to you a couple more things because they are I think, pertinent. This first one is from a guy named Adam Frank, and he's a professor of astrophysics again at the University of Rochester. In his article, and it's entitled Coronavirus and Climate Change, the Pandemic is a Fire Drill for Our Planet's Future. So I thought this was really very germane to what's going on right now. So to quote him, climate change, like the COVID-19 pandemic, is going to push the networks that make up our civilization. But unlike the pandemic, its effects will be long-term. There won't be a vaccine to save us. Climate change will mean the emergence, will mean one emergency after another, year after year, as heat waves, floods, fires, and storms blow cascades of failures at our systems of civilization. Examples of these threats range from disruption of the global supply chains due to increasingly extreme weather, and we're going to talk about that in just a minute, to failure of food production and distribution networks as climate pattern shifts, to failure of investment networks as risk assessments and getting insurance becomes more difficult, end of quote. And yet another quote, and this is from Giulio Pogoletti, and I hope I pronounced his name right, which is in the Nature Conservancy magazine, fall of 2020. The article is titled The Power of Nature. And what he says, to quote him, "We are the fragile creatures, not nature, that have chosen to undermine the very foundations that keeps our homes from collapsing. We are the unwitting victims of our own success. And if we are going to survive, we need to turn to nature for the answers." End of quote. To put my own spin on this then, do you remember the heat wave we had in mid-August of 2020? Temperatures at my place, my home, here in the foothills of the Sierra Nevada, topped 107 degrees Fahrenheit. Or how about the shorter heat wave in early September 2020, when temperatures at my house actually hit 108 degrees Fahrenheit. They were held down then only because of all the persistent smoke from all the wildfires burning throughout the state. These occurrences are not one-offs. In the next 5 to 10 years, prolonged waves will be, heat waves will be much more common, and the temperatures they produce will be higher. Spikes in temperature to 115 degrees may not be common, but they will not be unusual either. A report on the internet dated September 10th, 2020, which was yesterday, states that 2020 has been a terrible year for weather and fire. Oh yeah? Not to mention the pandemic. But in 10 years, we will probably look back and say those were the good old days when disasters weren't really so bad. It's going to get a lot worse. The 2030s are going to be noticeably worse than the 2020s. And I hate to be the bearer of bad news, folks. I know it's already bad enough, and then I'm piling stuff on top of you on top of stuff. Okay, so let's look then at the very last thing we have today, and that's something called how climate change can affect life. And this is a very classic example, and it's the Viking Greenland settlements. So the Viking settlements of Greenland started about 1000 AD during a warm period known as the medieval warming period. Great name there. At their peak, there were 2 colonies totaling about 3,000 settlers between about 1200 to 1250. After that, the colonies began a gradual decline with the abandonment of the northern colony first and the southern colony in the mid-1400s. What is referred to as the Little Ice Age began about 1250, and it lasted for 600 years, all the way up to 1850. During this period, worldwide temperatures were well below the preceding years, and there were reports from Europe of years when there was no summer. Crop failures were common. Temperatures dropped, weather systems became more erratic, storms grew more frequent and severe, and the trade route between Greenland and Iceland and on to Bergen, Norway became even more treacherous than it already was. Remember, we just talked about the disruption of trade? okay? To compensate, the settlers shifted from cattle and pigs to mostly sheep and goats, as it became more difficult to provide forage for the larger animals. And sheep and goats were better able to withstand the increasingly cold temperatures. Crops also became more problematic. And the crops they were growing then were our winter vegetables, cauliflower, not cantaloupe, cauliflower, broccoli, uh, kohlrabi, those kinds of colder crops. They could grow those, but now even that was becoming problematic, and that then resulted in increased imports and in higher costs to support the colony. Now they also hunted seals, walrus, caribou, and they fished, and that was still okay. So as you can see on the slide then, the Little Ice Age was not the only factor in the collapse of the colonies, though it was probably an important one. It probably produced a spark that pushed the colonies beyond that tipping point we've talked about as mounting pressures accumulated. The settlement lasted for about 200 years after the onset of the Little Ice Age, but by the early 1400s, they were becoming increasingly unsupportable, and by the mid-1400s, the last settlement was gone. So before we move on, I'd like to tell you, in fact, we aren't going to move on very far, we're about at the end here. But before we move on, I'd like to tell you another more modern day story of how climate change, in this case warming, has impacted the tourist trade. So let's go back to the early 19th century, or 1900s, pick a date, 1905, 1906, I don't care, whatever date you want. And you go into the local Princess Cruise office and you say to the person there, you say, I want to take a cruise up the inland passage, inside passage, from Vancouver up to Alaska. And on the way, I want to stop and see Glacier Bay and College Fjord. I really want to see those. And the representative said, well, fine, we run cruises up the inside passage all the time, but I'm a little puzzled because I've never heard of Glacier Bay or College Fjord. So now it's 2015, 2016, I don't care, 2005, whatever date you want to pick again. You walk into the same office, probably talk to a different person, and you tell them the same thing, inside passage, College Fjord, Glacier Bay. And the guy says, not a problem. We routinely stop at both of those points and sail into them. So the question is then, in about 100 years, what changed? In the early 1900s, there was no such thing as Glacier Bay or College Fjord. The glaciers then came right down to the coast. They were tidal glaciers, just like Thwaites. They were tidal glaciers. But with the warming of the oceans, that ice was gradually melted, and the glaciers, and the atmosphere too, and the glaciers began to recede, so that now we have Glacier Bay. You can sail into it, the glaciers come down the sides, and you can see them, but they aren't filling the bay. The same with College Fjord. The glaciers retreated up the fjord until now, I think you got to sail like 30 miles, or maybe it's 40 miles up the fjord to get to the head of the glacier, and that glacier is retreating every year. So to kind of close out then, I guess I would ask anybody who denies that global warming is occurring, I would ask only one question. What makes ice melt? Okay, and so that really concludes our presentation for today. We're going to, next week, we'll go on to part 5 and conclude our course. And part 5 is what you've been waiting for, what can be done. And we'll talk about some governmental initiatives that have been taken. We'll talk about some new technology that has promise, but mainly we're going to talk about what we as individuals can do, both in our gardens and around our house, to help mitigate the changes, okay? So that's where we're going, part 5. What you all been waiting for, what the title of the course suggests, all right? So in the meantime then, thank you so much for the privilege of your time, and I hope to see you again next week.